Have you ever wondered if the universe we think we know is actually just a shadow cast by the limitations of our own tools? What if the biggest discoveries of the last decade weren't new laws of physics, but rather the realization that our simulations have been tricking us all along? Welcome to a special update on the state of modern cosmology, where we dive into a fresh wave of research that is fundamentally reshaping how we understand everything from the birth of black holes to the very fabric of spacetime. Today, we are unpacking a series of groundbreaking studies that challenge old assumptions, reveal hidden numerical traps, and offer a clearer path forward for the next generation of astronomical exploration. Stay until the end, because the final revelation about what lies hidden in our supernova simulations might just change the way you view the reliability of scientific prediction forever. For decades, cosmologists have been navigating a sea of uncertainty, trying to piece together the history of the universe using fragmented data from light, radio waves, and gravitational ripples. The central problem facing the field today is a crisis of resolution and scale. On one hand, we have monumental questions about the nature of dark matter and the origins of black holes. On the other, we face the nagging suspicion that our most complex computer models might be producing results that are artifacts of the math itself, not reflections of physical reality. This tension has created a bottleneck where conflicting theories about neutrino masses, the alignment of our galaxy, and the behavior of merging black holes struggle to find a unified voice. Without a way to distinguish between true physical phenomena and the noise of coarse calculations, our roadmap for the cosmos remains blurred, leaving us unsure whether we are looking at the universe or merely a distorted mirror of our own computational limits. But now, a new suite of research is cutting through this fog, offering startling clarity. Imagine looking at a low-resolution photograph of a distant star. It looks like a smooth, fuzzy blob, but when you zoom in with a high-definition lens, suddenly you see distinct craters, shadows, and textures that were never there before. This is exactly what recent studies have uncovered in the realm of supernova simulations. Researchers have identified that previous models, using coarse grid resolutions, artificially triggered explosions and delayed the formation of black holes. These weren't real cosmic events. They were digital ghosts created by the roughness of the mathematical grid. By refining these simulations, scientists have separated true physical behavior from numerical artifacts, revealing that the universe is far more stable than our older models suggested. This breakthrough extends far beyond just fixing computer codes. In the study of black hole collisions, a universal linear relationship has been discovered between peak and final recoil velocities. Think of it like a cosmic billiard table where, no matter how hard you strike the ball or from what angle, the final speed always settles into a predictable rhythm. This simplifies the chaotic dance of merging black holes into a single scaling law, making it much easier to predict the gravitational waves they send rippling across the cosmos. Similarly, in our own backyard, new simulations of the Milky Way show that our galaxy's spin is not random, but aligns perfectly with its dark matter halo, a fingerprint left behind by a massive merger event billions of years ago. It is as if the galaxy remembers its own history, etched into the very angular momentum of its stars. Furthermore, the mystery of dark matter and neutrinos is coming into sharper focus. For years, the effective mass of neutrinos has been a source of tension in physics, but a new sign-switching model has resolved this, yielding a precise value that aligns beautifully with observational data. Even more intriguingly, studies of asteroid-mass black holes have used steady neutrino emissions to place a stringent upper bound on how much of the universe's dark matter these objects could constitute. The result is a stunningly small fraction, effectively ruling out the idea that these ancient, asteroid-sized black holes are the dominant form of dark matter hiding in plain sight. These findings do not just add data points. They act like a filter, straining out the impossible theories and leaving behind only the most viable candidates for the true nature of our reality. The implications of this paradigm shift are profound for both science and humanity. By moving away from isolated studies of single wavelengths and embracing a multi-messenger synergy, we are building a more robust framework where radio, optical, and gravitational data cross-calibrate one another. This approach allows us to prioritize specific targets for next-generation instruments like the SKA radio telescopes and the LISA gravitational wave detector. Instead, casting wide nets and hoping for a catch, we can now aim our instruments with surgical precision, focusing resources on the most promising windows of discovery. Moreover, recognizing the pitfalls of numerical artifacts serves as a crucial warning for engineers and physicists alike. It reminds us that in our quest to simulate the cosmos, we must remain vigilant against the seductive simplicity of low-resolution models that might lead us to false conclusions about safety-critical phenomena like supernova explosions. Ultimately, this convergence of high-fidelity simulation and multi-messenger observation is narrowing the search space for new physics. We are no wandering blindly through infinite possibilities. We are mapping a constrained landscape where modified gravity and dark matter candidates are confined to testable, narrow windows. This precision enables a more efficient allocation of human curiosity and technological investment, ensuring that our next great leap forward is built.